Good morning. I am Professor Somayajulu from NIT Warangal. In the earlier lecture, we introduced the importance of data pre-processing for building a data warehouse. In this lecture, we discuss different topics which are very widely used while pre-processing the data. They are data transformation, data reduction, data integration, data discretization, and concept hierarchy generation. So the first topic is data integration and transformation. By understanding this topic, you are able to understand how to change the data from one form to other form. We also critically examine how correlation analysis is useful in detecting the redundancy among the data values. Data integration. The sources may include databases, data cubes, flat files, etc. When we combine the data from multiple sources into a coherent source. In fact, this coherent source we call as data warehouse. So while integrating the data, we use the integration of metadata first, which we call as schema integration. For example, there can be different names exist across two different sources for the same attribute. Customer ID name used to identify the customer in source A and customer number is used to identify the customer in source B. In such situations, without understanding the schema representation of the two sources, it is very difficult to integrate the sources. So that is why schema integration is very important here. In order to resolve the errors while integrating the data, metadata is widely used. The metadata is also used to help to transform the data. In fact, not only data warehousing but also data mining often requires data integration to find the frequent patterns from a large available data. It doesn't mean all sources are same type when we integrate the data from multiple sources. The sources may be different. Therefore, we need to combine them into a single schema. So there are several issues. As I mentioned, schema integration is one issue. We need to identify a strategy while combining the sources. The problem of entity identification is very much essential here while integrating the sources. In fact, this is a strategy used to combine the data. We use name equivalence to combine, but how can we equivalent real world entities, data sources be matched? So the matching is generally done by using entity identification. For example, customer ID in one database and customer number in another database refer to the same database. How exactly a computer or data analyst do compare? As I said earlier, to solve such problem, we use the metadata. Because the metadata keeps the details of each attribute like name, meaning of the attribute, the type of the attribute, range for the attribute values, and the null values. Such metadata helps to avoid errors while integrating the schema. During integration, we should also see that the data is not duplicated. Suppose if the data is duplicated, it leads to redundancy. So which can reduce the efficiency and leads to inconsistency. Therefore, redundancy is also needs to be controlled. When the attribute values are different for same real world entity, then how do we decide whether it is redundant or non-redundant? So, detecting and resolving data value conflicts is also an important issue which needs to be considered into account while integrating the data. Because the same real world entity may have different attribute values in different sources. And also the reason for having these kind of values may be because of possible representations used in each entity definition. For example, units may be represented in metric units in one source, whereas British units in another source, but both represent the same kind of data values. So how do we handle the redundancy in the data integration? Redundant data is an important issue that need to be taken into account while integrating the data. Inconsistencies in attributes, dimension naming can also cause redundancies in the resulting data set. If an attribute is derived from the other attributes, then the derived attribute is called redundant. For example, date of birth and age are two attributes present in a database. Age can be derived from the date of birth. Therefore, we can consider age as a redundant attribute. Then the question is, how do we detect whether the attribute is redundant or not? So to detect such redundancies, we generally use the concept called correlation analysis. That means to say, correlation analysis is useful in detecting the possible redundancies. Careful integration of data from multiple sources may help in reducing the redundancy or avoiding redundancies and inconsistencies. So ultimately it improves the mining quality and the speed to mine the result. That means performance of mining gets improved. Then what is correlation? How correlation is useful in detecting the attributes will be discussed now. Now the question is, how do we determine such coefficients? The correlation coefficient always lies between -1 and +1. But the question is, how do we compute? For numerical attributes, by using correlation analysis between the two attributes, we can determine how strongly one attribute implied the other on the given data. The correlation coefficient is also termed as Pearson's product moment coefficient, which can be computed by using the formula shown on the slide. The correlation coefficient is denoted by a symbol R. Here A and B are the attributes. N is the number of tuples. A bar is the mean of A. B bar is the mean of B. Sigma A and sigma B are standard deviations of A and B respectively. And sigma AB is the sum of the cross product of A and B. By using this formula, when we compute the correlation coefficient, this coefficient value tells about what kind of relationship exists between the one set of values, say A, with the another set of values B. The higher the correlation value, the stronger the correlation. It means that the more each attribute implies the other. Higher correlation value may indicate that the attribute A may be removed as a part of redundancy. So if the correlation coefficient is greater than 0, that means A and B are positively correlated. Positively in the sense, A's values increase as B value increase. That's why we call this as the higher the value, the stronger the correlation. Suppose if the correlation coefficient is equal to 0, then we call that the attributes A and B are independent. That means they are not correlated. And the correlation coefficient is negative, then we say that A and B are negatively correlated. Means that each attribute discourages the other. In fact, we can also use scatter plots to view the correlations between the attributes. Now for categorical data, we can use chi-square test to determine the correlation. For categorical, that means the discrete data, a correlation relationship between the two attributes A and B can be determined by chi-square test. Suppose if the attribute A has C distinct values, say A1, A2, etc., AC, the attribute B has R distinct values, say B1, B2, BR. The C values of A making up the column and R values of B making up rows. By using the formula shown on the slide, chi-square can be computed by using the counts, right? So the total values of A is equal to A, how many are there, with the product of count of B is equal to B. The larger the chi-square value, the more likely the variables are related. The cells that contribute the most to the chi-square value are those whose actual count is very different from the expected count. Correlation doesn't imply causality. If A and B are correlated, this does not necessarily imply that A causes B or that B causes A. While analyzing, suppose, the demographic database, we may find that attributes representing the number of hospitals and the number of car thefts in a region are correlated. That means we have identified a correlation coefficient close to 1 here, say. This doesn't mean that the number of hospitals causes the number of car thefts or the number of car thefts causes the number of hospitals. In fact, both are linked to a third attribute called population. So the more the population, more hospitals and more number of car thefts may happen. So now to discuss how chi-square test is applied, the slide shows a simple example related to chi-square calculation using the formula summation of observed minus expected squares by expected. By using this chi-square formula, if you do the computation, we can say that like science fiction and play chess are correlated in the group, as the calculated value of chi-square, say 507, is more than the significance level. This chi-square characteristic tests the hypothesis that A and B are independent. The test is based on a significant level with R minus 1 and into C minus 1 degrees of freedom. So therefore, by using this computation, we can always say that like science fiction and play chess are correlated in the group. So for categorical data, we use chi-square test. Data transformation. Data are transformed or consolidated into suitable forms which are appropriate for mining. There are different kinds of transformation methods which I have already discussed earlier. One is the smoothing method, which is basically used to remove the noise from the data. Then another method is aggregation, data cube computation, summarization. They are all helpful to reduce the data. Binning, regression and clustering also belongs to the category of smoothing methods. Then generalization, by replacing the low level attribute values with the higher level values as per the concept hierarchy, we can generalize the data. So this is also belongs to the category of transformation. Street is replaced by city or country. It means that the street value of every row of the database is replaced by either city value or country value. That means replacing the low level concept by high level concept. There is another kind of transformation called normalization. This is basically used to replace one set of values in a range to another set of values. Basically, it reduces the number of possible values in each range. The popular methods used for normalization are minimax normalization, z-score normalization, and normalization by decimal scaling. We discuss now each one of the method with an example. Minimax normalization is one kind of transformation which belongs to the category of linear transformation. The original data given in a range is replaced with new data set of values. Suppose min and max are the minimum and maximum values of an attribute A, then the min and max maps a value V of A to a value V dash in the new range. New min A, new max A. For example, income ranges between 12,000 to 98,000 are normalized to interval 0 to 1. So the normalization is done by using the formula. We know that minimum for A is 12,000, maximum of A is 98,000, new min A is 0, new max A is 1. And the value 73,000 is replaced to a value V dash in the range 0 to 1 by using the formula shown on the slide. If you substitute all the values in this formula, we get a V dash as 0.76. That means the value 73,000, which belong to the range 12,000 to 98,000, is replaced to 0.76 into the new range of interval 0 to 1. So this transformation definitely reduces the number of possible values from a given range to a new range. There is another kind of transformation called Z-score normalization. This is also termed as zero mean normalization because we are taking the deviation above the mean. Mean is represented here by mu and sigma is the standard deviation. Suppose mu is 54,000 and sigma is 16,000, then V dash for a given V 73,600 can be replaced with 1.225. So the values, that means here the values of the attribute A are normalized based on the mean and standard deviation of the attribute A. The third kind of method is called normalization by decimal scaling. Here every value of V is divided by some number 10 to the power of j, where j is the smallest integer such that maximum of V dash is less than 1. The j gives the index such that maximum of V dash is less than 1. So in that fashion we can replace every value of V into a V dash by taking the ratio of V with 10 to the power of j. So these data transformation methods, we can transform the data from one form to another form into a new interval, and this is definitely reduces the number of distinct values for each attribute. We also discussed in this topic how to integrate the data and how to resolve the schema integration problem. So basically both the methods ultimately gives you to detect the inconsistencies among the data values and also to identify what kind of redundancy exists among the data values. So in a way, correlation coefficient for numerical data as well as categorical data is helpful in detecting the redundancy. The next topic, data reduction. Data reduction is a reduced representation of the data set that is much smaller in volume but yet produce the same analytical results or almost the same analytical results. A database or a data warehouse consists of terabytes of data. In order to make complex data analysis practical or feasible, there is a need to reduce the used amounts of data for ready to mine using the concept of data reduction methods. These reduction methods produces a reduced representation of the data which is lesser in volume and maintains closely the integrity of the original data and ultimately produces approximately equivalent analytical results. The various strategies that exist in the literature for data reduction are data cube aggregation, dimensionality reduction, data compression, numerosity reduction, and discretization and concept hierarchy generation. Data cube aggregation. Aggregation operations are applied to the data in the construction of a data cube. It stores multidimensional information. Presence of concept hierarchy help to compute aggregation at multiple levels. These data cubes provide fast access to pre-computed summarized data, thereby benefiting OLAP and data mining. The lowest level of data cube is called base cuboid. The highest level of cuboid is called apex cuboid. So in each data cube, we can have multiple levels of aggregation to reduce the size of the data further. For example, a customer in a phone calling data warehouse. For this data, we can build the data cube by individual entities of interest, and by applying the aggregation, we can find different kinds of aggregations using a customer phone call data warehouse. In this approach, aggregation operations are applied to the data for building a data cube. But in fact, data cubes are multidimensional aggregated information. That means it stores different aggregation information. Each cell in a data cube holds an aggregate data value corresponding to the data point in the multidimensional space. It also allows analysis of data at multiple levels. So to do that, we use the concept of concept hierarchy for each attribute. These cubes provide fast access to pre-computed summarized data. Data cubes created for varying levels of abstraction are termed as cuboids. In view of this, data cube can be viewed as lattice of cuboids. Each higher level abstraction reduces the resulting data size. We can also perform queries on aggregated information using data cube whenever it is required. The second method is attribute subset selection. Attribute subset selection is a strategy basically help to identify automatically the most important or essential attributes out of several attributes for a given data set. That means this process eliminates irrelevant attributes or redundant attributes from the database. The goal of the attribute subset selection is to find the minimum set of attributes such that the resulting probability distribution of the data classes is as close as possible to the original data distribution obtained using all attributes. The advantage of this process is it reduces the number of patterns and also understanding of patterns is easy. Due to exponential number of choices exists for a given n attributes, heuristic approaches are used to determine best subset of attributes. The different kinds of heuristic methods for solving attribute subset selection problem are stepwise forward selection, stepwise backward elimination, combining of forward selection and backward elimination, and decision tree induction. These methods are useful for determining the optimal number of attributes, which we call as features. Optimal number of features. In the case of stepwise forward selection, we start with an empty selection and add best attributes one after the other. That's why it's called forward selection. Whereas in the case of stepwise backward elimination, we take all the attributes initially and then we eliminate the less informative attributes from this set recursively. That is why it is called backward elimination. And if we use forward and backward combinedly, then we say that it is a combined forward and backward elimination. So for example, the slide shows a simple tree. Suppose if we have 6 attributes A1, A2, A3, A4, A5, A6, to identify the features that are essential to determine the class label, say class 1 or class 2, this structure takes minimum of 3 attributes. So out of 6 attributes, only 3 attributes are sufficient to determine the class. So first we compare, we divide the data by taking the attribute value A4, then we get distinct classes, 2 groups, then again in each group the attribute A1 is used to determine the class label, whereas in the other group attribute A6 is used to determine the class label. So therefore, if we combine all the attributes used in this tree, we get a set of 3 attributes A1, A4, A6, which is a reduced representation of the initial attribute set. So in the case of best stepwise feature selection, we consider, as I mentioned earlier, the best single feature is picked first, then the next best single feature is picked next, etc. Whereas stepwise feature elimination, worst feature is eliminated first, the next worst feature is eliminated next, like that. Then we can use backtracking and also we can use feature elimination method to determine the optimal branch and bound structure for feature selection method. Another kind of strategy for data reduction is data compression. In fact, there are extensive theories and well-tuned algorithms exist to compress the strings, but whenever we compress the data, it should be typically lossless compression, but we can only do limited manipulation without expanding the compressed data. Whereas if you take audio compression or video compression, typically they are lossy compression with some refinement. Sometimes small fragments of signal can be reconstructed without reconstructing the whole, and typically time sequence is not an audio, and that's very short and very slow, very slowly with time. So if you observe the figure, the original data is compressed and stored in a database which we call as a compressed database. The compressed data, if you reconstruct the original data completely, then we call this as a lossless. If you are only approximating the original data, I repeat, if we get only the approximated original data by decompressing, then we call this as a lossy compression. Dimensionality reduction. In dimensionality reduction, we produce a reduced representation of the original data by applying certain data encoding methods or transformation methods. Data reduction produced using this may be lossy or lossless. If the original data is reconstructed from the corresponding data without any loss of information, as I mentioned earlier, is termed as lossless. otherwise it is lossy. There are several methods exist in the literature, but we concentrate only the two popular methods related to lossy dimensionality reduction, namely Wavelet transformation and principal component analysis. Wavelet transformation is a signal processing method. This method takes data set and viewed as a data vector x as input and produces numerically different vector x dash of wavelet coefficients as output. Both vectors x and x dash are of same length. Here x is viewed as an n-dimensional data vector. Due to truncated nature, Wavelet transformed data reduced data representation. By considering user-defined threshold, all wavelet coefficients larger than the user-specified threshold will be retained and all coefficients less than the user-defined threshold are set to 0. In view of this, data representation is very sparse. Operations on sparse data can be performed very fast compared to non-sparse data. This method is also suitable for removing noise without smoothing out the main features of the data. Also, using inverse transformation method, from a given set of coefficients, an approximation of the original data is constructed. This approach is used also for multidimensional data sets such as data cubes. First we transform the first dimension, then to the second dimension, and so on. The computational complexity involved is linear with respect to the number of cells in the data cube. Wavelet transforms provide good results on sparse data or skewed data and data on ordered attributes. So the method works like this. Length L must be an integer power of 2. So if it is not an integer power of 2, then we can pad with zeros if required. Then each transform has two functions, smoothing and difference. And this method is applicable to pairs of data resulting two sets of data of length L by 2. Until it reaches the desired length, we apply the two functions recursively. Another method is called principal component analysis. This method locates for k n-dimensional orthogonal vectors that can be best used to represent the data. Here k is always less than the number of data points, number of data attributes. So that means this method finds the best k orthogonal vectors, which we termed as principal components, that can be used to represent the data. This way the original data is projected onto much smaller space, which results in dimensionality reduction. This method combines the essence of attributes by creating an alternative smaller set of variables. Principal component analysis is computationally inexpensive and can be applied to ordered attributes as well as unordered attributes. This also handles sparse and skewed data. Principal components can also be used as inputs to multiple regression and cluster methods. So this is a better approach for handling sparse data, whereas wavelet transforms method is suitable for data of high dimensionality. So the steps of determining the principal components are shown on this slide. First we normalize the input data. Each attribute falls within the same range. That must be ensured here by using the normalization process. Then we compute k orthonormal vectors. These orthonormal vectors are called principal components. Each input data is a linear combination of the k principal component vectors. That means we express each data element is a linear combination of these k principal component vectors. Principal components are sorted in the decreasing order of their significance or strength. Since already the components are sorted, the size of the data can be reduced by eliminating the weak components. That means those components with low variance gets eliminated. So using the strongest principal components, it is also possible to reconstruct a good approximation of the original data. But of course, this method is very widely used only for numerical data. And also when the number of dimensions are large, we can apply this principal component analysis approach for data reduction. So the slide shows the components, how the principal components identifies the orthonormal vectors. Here there are two vectors which are shown as orthonormal vectors, which we consider as the principal components. Then the next approach is numerosity reduction. This technique also reduces the data volume by choosing alternative smaller forms of data representation, and these are categorized into two ways. One is the parametric method and another is the non-parametric methods. In parametric methods, we assume the data fits some model and estimate the model parameters, and finally we store only the parameters and discard the data. Log linear models is an example for parametric method. It obtains a value at a point in an m-dimensional space as the product on the appropriate marginal subspaces. Whereas in the case of non-parametric methods, we do not use any models, but we use histograms, clustering and sampling to store the reduced representation of the data. Regression and log linear models. Data in linear regression, data is modeled by fitting a straight line. While fitting the straight line, we use the popular least square method by considering a condition that the sum of the squares of the error is kept at the minimum. In the case of multiple regression, a response variable y is modeled as a linear function of multidimensional feature vector. So in parametric methods, we store only parameters instead of actual data. So the slide shows linear regression and log linear models. Y is equal to wx plus b. Here we approximate the values of w and b, and then we store only for a given value of x what is the approximate value of y. The two coefficients w and b specify the line and are to be estimated by using the data at hand. That means for a given set of points x1, y1, etc., xn, yn, we estimate the coefficients of w and b in such a way that the sum of the squares of the error is kept at the minimum. Using the least square criterion, we minimize the error. In the case of multiple regression, we have multiple set of variables. Here x1 and x2 are two variables. Y is expressed in terms of x1 and x2. So in this case, we estimate the coefficients b0, b1 and b2 in such a way that the sum of the squares of the error is kept at the minimum. The multivariate table of joint probabilities is approximated by a product of lower order tables in the case of log linear models using the probability calculation. Another kind of data reduction method which belongs to the category of non-parametric kind is known as histogram. Histograms divide the data into buckets and store the average for each bucket. Of course, we can use either equal width partitioning or equal frequency partitioning. Equal bucket range is taken in the case of equal width partitioning, whereas equal depth, the occurrences, based on the occurrence of values, we use equal frequency approach, partitioning. With the least histogram variance, we can also find the optimal value in the sense that by taking the weighted sum of the original values that each bucket represents. Maximum difference is another parameter rule considered into account here. We can set the bucket boundary between each pair of. So basically, whenever we plot an histogram, the frequency of each, the interval and the number of occurrences of. Then another data reduction method is called clustering. In clustering, we partition the data into different clusters based on the similarity measure and store only the cluster representation. That means centroid and the diameter are basically the two parameters used to represent the cluster. This approach can be very effective if data is clustered but not if data is smeared. Of course, we can also have hierarchical clustering, and we can store these hierarchical clusters in a multidimensional index structure. There are many choices of clustering definitions and algorithms exist in the literature, but ultimately cluster analysis helps you to identify the optimum number of clusters such that all the elements within the cluster are highly similar and the elements across the cluster are highly dissimilar. Another kind of data reduction method is known as sampling. Sampling process obtains a small sample S to represent the whole data set N. This method allows a mining algorithm to run in complexity that is potentially sublinear to the size of the data. So normally we choose a representative subset of the data. Sometimes simple random sampling may have very poor performance in the presence of skewed data. An adaptive sampling approach, one such method is called stratified sampling. In this method, we approximate the percentage of each class or subpopulation of interest in the overall database. This approach can also be used in conjunction with the skewed data. Of course, sampling may not reduce the database IOs. It identifies only a representative subset of the data. Replacement or without replacement. The slide shows the two different kinds of differences. Simple random sample without replacement, whereas simple random sample with replacement. Also use clustering or stratified sampling approaches to determine the reduced representation of the data. Here, for example, the raw data is clustered into 3 clusters, but some of the elements within each cluster are removed by using the stratified sample. So that means you have identified the elements in such a way that all the elements in each cluster provides the reduced representation for all the elements within that cluster. We now discuss the last topic of today's lecture, namely discretization and concept hierarchy. The objective of discussing this topic is to know how to generate the concept hierarchy for numerical data, and also how to generate concept hierarchy for categorical data based on the number of distinct values of attributes in a database schema. Discretization and concept hierarchy methods are also part of preprocessing. The main advantage of using these techniques is that mining and reduced representation of data needs less number of inputs or output operations and is more efficient than mining on large non-generalized data set. Discretization generally uses different kinds of attributes. The attribute may be a nominal type where the values form an unordered set, for example color, profession, etc. Or it can be ordinal where the values form an ordered set, academic rank or organizational hierarchy belong to this category. Or it can be continuous where real numbers, integers or real numbers. Each continuous attribute is divided into various intervals by taking its range, and each interval is named with a label called interval label while discretizing the data. This way, several values which belong to a particular interval of a continuous attribute is replaced with the corresponding interval label. This process simplifies and reduces the original data. And finally, this process also provides easy to use and knowledge level representation of mining results. So in a way, the discretization also belongs to the category of data reduction. It prepares further the data for analysis. Concept hierarchy is also another kind of discretization process. Discretization methods, if the class information is not used, then the discretization methods are termed as unsupervised discretization methods. You can apply discretization process either in a top-down manner or bottom-up manner. In the top-down discretization, we use the split approach. In this, the process starts by identifying one or few points called cut points or split points to divide entire attribute range, and this process gets repeated recursively on the resulting intervals. Whereas in the case of bottom-up discretization, the process starts by considering all continuous values as potential split points, some split points by merging neighborhood values to form intervals. This process gets repeated recursively to the resulting intervals. Concept hierarchy for a given numerical attribute also defines discretization for that attribute. So it recursively reduces the data by collecting and replacing low-level concepts by higher-level concepts. For example, numerical values for age attribute may be replaced in each row by higher-level concepts as young, middle-aged or senior people. Another example for concept hierarchy based on discretization is, suppose if you have a marks attribute and the values of marks attribute which can be replaced with high-level concepts such as excellent, good, satisfactory and fail. And if we replace, definitely it will minimize the number of distinct values for attribute marks. This type of generalization is more meaningful and easier to interpret, although we lost the original data. The advantage of this approach is that it provides consistent representation of data mining results among multiple data mining tasks. Concept hierarchy can be generated either manually or automatically. Automatic generation of concept hierarchy for numerical and categorical attributes is less tedious and consumes less time for a domain expert or a user, whereas manual generation of concept hierarchy is laborious and consumes more time. Also, many concept hierarchies for categorical attributes are implicit within the database schema and so it can be automatically generated at the schema definition. In view of the above facts, concept hierarchies for numerical attributes can automatically be generated based on the data discretization. Now the question is, can we generate concept hierarchy manually? So the answer is yes, it is possible to generate, but it requires a lot of time and a tedious process. You know why is it difficult? Ranges for each attribute may be very wide and we update database very frequently. Due to these reasons, manually defining concept hierarchy is tedious. But for numerical data, methods exist for automatic generation of concept hierarchy or dynamically to refine the concept hierarchy. In fact, many hierarchies for categorical attributes are implicit within the database schema and can be automatically defined at the schema definition level. Now we discuss different kinds of discretization methods. Typical discretization methods are binning methods, histogram analysis, cluster analysis, entropy based discretization, and discretization by intuitive partitioning. Binning methods. Top-down split techniques based on a specified number of bins are used here. Since binning approach is not using any information related to class information and it is belong to unsupervised class of methods. These methods are sensitive to number of bins specified by user and also sensitive to presence of outliers. In fact, in the earlier lecture, we discussed various smoothing methods for binning. Methods are also useful for generating concept hierarchies. Histogram analysis. This approach also belongs to unsupervised since this approach doesn't use any class information. This approach partitions each attribute value into disjoint buckets, and this approach also belongs to top-down split and unsupervised class. We now discuss histogram analysis. Basically, histograms are useful to approximate the data distribution. For generating histograms, we will use partition rules. In equal width histogram, the values are partitioned into equal sized partitions. For example, marks attribute can be partitioned into 4 intervals with width as 24. Whereas in the case of equal frequency histogram, the values are partitioned so that each partition contains the same number of data tuples. By applying the histogram analysis approach recursively to each partition, we can automatically generate concept hierarchy with multi-level. Of course, we can also use the minimum interval size per level to control the recursive procedure. Minimum interval size specifies either minimum width of a partition or minimum number of values for each partition at each level. Based on cluster analysis of data distribution also, you can partition the histogram. So the slide shows a histogram for a unit price by partitioning into different intervals. The histogram consists of set of rectangles that reflect the counts or frequencies of the classes present in the given data. Then the other kind of method is known as entropy based discretization. The next method is called cluster analysis. Cluster analysis also uses either a top-down split or bottom-up merge approach, and also it belongs to the category of unsupervised. All the methods, namely histogram methods, binning methods or clustering analysis methods, can be applied recursively to generate the concept hierarchy. Each method in general assumes that the values discretized are sorted in ascending order. Other kind of methods are entropy based discretization, interval merging by chi-square analysis, and segmentation by natural partitioning. We now discuss each method in detail. Entropy based discretization. Entropy is one of the commonly used technique for discretization measure, and it belongs to the information theory and is based on the concept of information gain. Entropy based discretization is a supervised and top-down splitting method. This method explores the class distribution information in calculating and determining split points. Here, data values are partitioned based on the attribute range. Given a set of samples S, if S is partitioned into 2 intervals, say S1 and S2, using the boundary T, here the boundary T can be considered as a split point, the information gain after partitioning is calculated with the formula shown on the slide. I of S comma T is equal to the ratio of number of values that are there in S1 with the total number of values S with the entropy of S1 multiplied with the entropy of S1 plus the ratio of the total number of values that are there in S2 with the total number of values in S multiplied with the entropy of S2. Entropy is calculated again based on the class distribution of the samples in the set. Given m classes, the entropy of S1 is calculated using the formula shown on the slide. Here Pi is the probability of class I in S1. To discretize the numerical attributes A, this method selects a split point which has a minimum entropy and recursively partitions the resulting intervals to arrive at a hierarchical discretization and forms finally the concept hierarchy for attribute A. So the boundary or the split point may reduce data size and improve the classification accuracy. In fact, the recursive process is stopped when some stopping criteria is met. Now we discuss the different steps. The class level attribute defines the class information per tuple. The basic method for entropy based discretization consists of 3 steps. Each attribute value of A is taken as interval boundary or split point to partition range of A. That is, a split point for A can divide the tuples in D into 2 subsets, satisfying conditions that A less than or equal to split point and A more than split point respectively. This step helps us in creating a binary discretization. That means we are dividing the database into 2 parts. All the rows where the attribute value A is less than or equal to split point as one group, and all the attribute values of A is more than the split point as another group. In step 2, entropy based discretization uses the information regarding class label of tuples. Suppose we want to classify the D by partitioning on attribute A and some split point. What we need to determine is the split point in such a way that it separates the tuples of D into 2 disjoint classes. That is, it should return exact classification. This is an ideal situation. For example, with respect to D, all tuples to say class C1 will fall into one partition and all tuples of class C2 will fall into another partition. This is not always possible because first partition may contain some tuples of C1 as well as some tuples of C2. The question is, how much more information is needed further for perfect classification after this splitting? This we termed as expected information requirement. The expected information requirement of database D based on the attribute A is computed using the formula shown on the slide in step 2. Number of values in D1 by number of values of D into entropy of D1 plus the number of values of D2 by the number of values of D into entropy T2. Here D1 and D2 correspond to tuples of D satisfying the condition that A is less than or equal to split point and A is more than split point. D is the number of tuples in D are denoted with cardinality of D. The entropy function is calculated based on the class information of the tuples in the set. For example, for a given m classes say C1, C2, C3, etc. Cm, the entropy of D1 is shown on the slide. Here entropy of Di is calculated with minus sigma I is equal to 1 to m Pi log to the base 2 of Pi. Here Pi is the probability of class Ci in D1, determined by dividing the number of classes of Ci in D1 by the total number of tuples in D1. Therefore, when selecting a split point for attribute A, we are interested in picking of the attribute value that gives the minimum expected information requirement. So, this result is still how much minimum amount of expected information needed to perfectly classify the tuples after partitioning by A less than or equal to split point and A more than the split point. This ultimately equivalent to the attribute value pair with the maximum information gain. Similarly, we calculate the entropy of D2. We use the split point to partition the range of A into 2 intervals corresponding to this split point. So in a nutshell, step 2 basically determines the expected information requirement for classifying the tuple. Step 3 is a stopping condition. I repeat, step 3 specifies a stopping condition. Stopping condition used here is that minimum information requirement on all candidate split points which is less than some minimum threshold, or when the number of intervals is greater than a a threshold called max interval. This approach reduces the data size. Since it uses class information, it belongs to supervised approach. Interval boundaries or split points are defined to occur in places where it can give better classification accuracy. The next method is interval merging by chi-square analysis. So the methods discussed so far are based on top-down splitting strategy, where this approach belongs to bottom-up merge strategy. That means interval merging by chi-square analysis is a bottom-up merge approach. And also it belongs to supervised because it uses class information. 3 conditions are used in this approach as a stopping criterion. Merging stops when chi-square values of all pairs of adjacent intervals exceed some threshold, which is generally determined by specified significance level. Very high value of significance level for chi-square test may cause over discretization, and very low value may cause under discretization. That is why significance level is generally chosen between 0.10 and 0.01. The second condition is related to the number of intervals cannot be pre-specified. For example, max interval here cannot be pre-specified here. And the third condition is relative cross frequencies should be fairly consistent within an interval. Some consistency is allowed in practice, but within the pre-specified interval, I repeat, within the pre-specified threshold, which is estimated from the training data, generally we use 3% of data. This helps to remove irrelevant attributes from the data set. So this method starts like this. Each distinct value of numerical attribute A is considered to be in one interval. Then chi-square tests are performed for every pair of adjacent intervals. Adjacent intervals with the least chi-square values are merged together, since low chi-square values for a pair indicate similar class of distribution. The merge process proceeds recursively until a predefined stopping criterion is met, which we have defined earlier, the 3 different kinds of stopping conditions. So using these 3 conditions, by following these 3 conditions, the merge process proceeds recursively until these 3 conditions are met. The methods discussed so far are useful for determining numerical hierarchies, but many users may be interested in viewing the numerical ranges partitioned into relatively uniform, easy to read intervals that appear natural or intuitive. For example, salaries of employees, annual salaries may be divided into ranges like 75,000 to 85,000 rupees, are often more desirable than ranges like 76, 774, 85,102, obtained by some cluster analysis approach. In general, the rule partitions a given range of data into 3, 4 or 5 relatively equal width intervals recursively and level by level based on the value range at the most significant digit. By applying these rules recursively for each interval, ultimately give a concept hierarchy for the given numerical data. The rules are shown on the slide. If an interval covers either 3 distinct values or 6 distinct values or 7 distinct values or 9 distinct values at the most significant digit, partition the range into 3 equal width intervals for 3, 6 and 9 distinct values and 3 intervals in the grouping of 2, 3, 2 for 7 distinct values. Suppose if it covers 2, 4 or 8 distinct values at the most significant digit, partition the range into 4 equal width intervals. If it covers 1, 5 or 10 distinct values at the most significant digit, partition the range into 5 equal width intervals. So these rules are followed in determining the partitions. Real world data is often tend to contain extremely large positive and negative outlier values. These values may distort any top-down discretization. These values may distort any top-down discretization method based on minimum and maximum data values. For example, annual income of a few people may be several orders of magnitude higher than those of others in the same data set. If you perform discretization on maximal data values, may lead to biased hierarchy. Hence, discretization must be done on some range of data values representing majority of the given data. The extremely high or extremely low values beyond the top level discretization must be handled separately but in a similar manner. That is, we consider data between 50th percentile and 95th percentile of the data. So that means to say we eliminate unnecessary interval with partitions for extreme situations. Suppose a user desires the automatic generation of a concept hierarchy for attribute profit, say. From the readability point of view, we use the notation, interval notation, L comma R represents the interval, open interval LR. For example, minus $10 lakh to $0 denotes the range from minus $10 lakh exclusive to $0 inclusive, to $0 inclusive. Suppose that the data within the 50th percentile and 95th percentile are between the range, say this one and this one. This is the high value and this is the low value. So instead of taking all the data values, extreme values on the left side and the extreme values on the right side are dropped by considering 5th percentile and 95th percentile as low and high values. So we want to partition the data in a natural way, all the profit values which lies between the 5th percentile and 95th percentile data. Using this information, the minimum and maximum values are considered for the attribute profit, and the low 5th percentile and high 9th percentile values to be considered for the top or first level of discretization. By setting the low value as minus $159 and high value as minus 1,838 millions. So in fact these numbers are rounded here. So rounding the low down to the million dollar digit, we get low dash as minus 1 million, and rounding high up to the $1 million digit, we get high dash as plus $2 million. Since the interval ranges over the three distinct values at the most significant digit is 3, the segment is partitioned into 3 equal width segments according to 3-5 rule. So the most significant digit is taken as $2 million minus of minus $1 million by $1 million, that is 2 plus 1, 3 by 1, that is 3. So since the most significant digit is 3, we divide the data into equal width segments according to 3-4-5 rule. Minus $1 million to $0 as one interval, $0 million to $1 million as the second interval, and $1 million to $2 million as a third interval. This represents the top tier of the hierarchy. So this is the top tier of the hierarchy. Top tier of hierarchy is represented here. This interval is decided, the number of intervals is decided based on 3-4-5 rule. By further examining each interval recursively, we can find out different kinds of intervals for each subinterval of step 3. So this way, by recursively using each interval, I repeat, this way recursively each interval can be further partitioned according to 3-5 rule for the next lower level of the hierarchy. So this is an example for numeric concept hierarchy generation by intuitive partitioning. So the intuitive partitioning is done based on these rules only. Concept hierarchy generation for categorical data. Categorical data are discrete data and have finite but possibly large number of distinct values with no ordering among the values exists. Geographic locations, say item types, job categories, they are all examples of categorical data. Several methods exist for concept hierarchy generation for such kind of data. They are grouped into 3 different kinds. In the first method involves a group of attributes. User defines here a partial or total order of the attributes at schema level. For example, location dimension as a concept hierarchy. Set of streets is a city. Set of cities constitute a state. Set of states constitute a country. So some kind of containment relationship is used here to hierarchically organize the several street values of various cities across the states in a country. Whereas in the second case belong to manual definition of a portion of a concept hierarchy. Basically, this type of mechanism is used to define explicit groupings for a small portion of the intermediate level of the data. For example, Andhra Pradesh, Karnataka, Tamil Nadu, they are part of India or southern India. So this is the explicit grouping we are doing of different states of a country, India. In the third method, a user may specify a set of attributes forming a concept hierarchy but omit to explicitly state their partial ordering. In such a case, system generates attribute ordering to construct a concept hierarchy. For example, only street precedes city, not others. So therefore, in such situations, we should have a mechanism to automatically generate the concept hierarchy by analyzing the number of distinct values. For example, for a set of attributes, street, city, state, country, we can analyze how many distinct streets are there, how many distinct cities are there, how many distinct states are there, how many distinct countries are there. So by doing this, by analyzing this, we can find automatically a concept hierarchy generation. For example, by analyzing the attribute values in a database over street, city, province, state, province, state, province or state or country, suppose if there are 15 distinct values for country and 365 distinct values for province or state and 3,567 distinct values for city and finally 6,74,339 distinct values for street exists in your database, then we can generate automatically the concept hierarchy by arranging the number of distinct values of each attribute in the increasing order, and then you put the highest level attribute having the lowest number of distinct values as a root node in the concept hierarchy. That is, the attribute with the most distinct values is placed at the lowest level of the hierarchy. Here the most number of distinct values that exist for the attribute street. That is why we are keeping at the lowest level. We repeat the process recursively to arrange the hierarchy. Of course, there can be some exceptions exist for the time dimension, weekday, month, quarter, year. In this situation, there will be 7 days, but months are 12, but number of quarters are 4. Year may be any number. So, but this is an exception as far as the automatic generation of concept hierarchy is concerned. So that is to say, some hierarchies can be automatically generated based on the analysis of the number of distinct values per attribute in the data set. So this way we can generate the concept hierarchy automatically by just computing the total distinct values for each attribute and placing the maximum number of distinct values that exist for an attribute at the lower level and placing the lesser number of distinct values of the attributes at the higher level. In this lecture, we discussed 3 different topics, namely data reduction, data transformation and normalization, and concept hierarchy for numerical data as well as for categorical data. So all these methods are part of data pre-processing. These methods are to be applied in designing a data warehouse. We need to appropriately choose the methods for reduced representation of the data. Thank you.